Okay. Now I'm going to talk about the surface integral. Surface integral, okay, given given a surface, right? And if you have a function on the surface, but this surface is covered by a domain in the two-dimensional, okay, coordinate plane. Okay, so this is a surface. Let's call the S. Okay, this is the image of this domain D. Okay, then if you have a function in the three-dimensional space or on the surface, then this integral of the function, okay, over the surface can be evaluated as using a double integral. And this f, okay, and then there's addition term, ds is going to be, this is a ds, okay? This is an area, we call the area element. Okay, so that is a formula. Okay, and in particular, okay, the area of S is just the integral of the function 1. Okay, so this is just the double integral of. Okay. Okay, that's it. So now we take a look at the problem. I think it's 11. Okay. 12. Okay. Let's find the area of the surface. Okay. This surface, it's hard to draw it given by this equation. The lines are within the cylinder. Okay, x squared plus y squared equals 1. Okay. Now, how do you solve this problem? I wanted to draw the picture a little bit, okay? So this cylinder, at least draw a cylinder. Okay. And z equals x times y. That means somewhere it's negative, somewhere it's positive. So when both x and y are positive, right? Somewhere here, it goes like this. It's hard to draw it, but this surface, some portions above the xy plane, some portions below the xy plane, because z could be negative. If x is negative, y is positive, right? So in the first quadrant, in the second quadrant, it's negative. In the third quadrant, it's positive. Anyway, something like that, okay, this surface. Okay. So the surface actually is a graph in this particular case. Now for the graph, you have a special parameterization, okay? For the graph, okay, we know that, we still use the xy, right? For the graph, it's x, y, f of x, y. Okay, so this product is going to be negative of x, negative of y, simple one, right? And the 1. Okay, so the ds is going to be the length, okay, of this product, cross product. It's going to be fx squared plus fy squared plus 1 dA, okay? Okay, so all I have to do is find out the derivative, okay, for the function, if fxy equals x times y, right? Then ds is going to be the derivative of x with respect to y. X derivative with respect to x, the derivative of y, f with respect to y, and the 1 and the dA. Okay. So the area of the surface inside a cylinder is going to be this W integral over d, okay, square over x squared plus y squared plus 1 dA. Now d is a disk, okay? D is a disk. This is the intersection of the cylinder with the xy plane, right? So that is a D. So D is this part, you know, the D is this part. Okay, that is a D. Okay. Then when you see this, it's pretty standard, use the polar coordinates, right? So you should, when you give a complete solution, you should write down the polar coordinates. Okay, and then this is will be, you know, eyes are between. Sometimes I write like that. I is between this, theta is between 0 and 2 pi. Okay, and here is going to be, here's r squared plus 1. That's r and d. You know, dr d theta. Okay, d theta d. Dr doesn't matter. Okay, so anyway, so let's evaluate with respect to theta. First, right? Theta is outside, r is inside, right? Okay. And so you have to use the substitution. So d equals half of dr. No. Yeah. d is 2r dr. So the antiderivative is u to the 1/2. Now the function is u to the 1/2. This is half of du. U start from 1 to 2. Okay, and d theta. Oops. This is weird. Okay. Okay. Yeah. So yeah, you just use a substitution, and yeah, that's du. Use from 1 to 2. Okay, don't forget change this part. Then you find the antiderivative. The antiderivative of this function will be here's 1/2. Here's 2/3. U to the 3/2. Right? When you differentiate, you get u to the 1/2. Okay. And we're almost done, right? So it's going to be 1/3 and 2 to the 3/2 minus 1 to the 3/2. And then this is the integral. Oh my God, I don't know what has happened. Sorry for that. Something's wrong with this again. It's pretty unstable. Okay, let's continue. All right. Then you will get, just put 2 pi on the top. Okay, that's it. So this is Yeah, this is just a surface integral. Okay, all you have to do is at the end, usually the domain could be a triangle, could be circle. If it's circle, use the polar coordinates, usually, right? Now, if you look at the part covered by test 1, we also have problems how to find the maximum value, minimum value. Okay, and here's a function. Okay, we are given a function, 2-variable function. Okay, we want to find the local, we call the extreme value. Okay, and the set point of actually the graphing, the graph of the function. Okay, so-called set points is those are special points, looks like that, and one side is going down, other side is going up. Okay, other side. So this is called set point. Okay, this is a point called set point. Set point. Okay, and those are called, local maximum point. Okay, right, and this is called local minimum point. Okay, so we want, and the value is different. Value is just a value. Okay, so if you know the local minimum point, then you of course you know the local minimum value. Okay, so how to do that? Well, if the function reaches a local maximum value or local maximum value, the necessary condition is the partial derivative is 0. So it's sufficient. Yeah, the first step, you have to find the critical points. Okay, so you have to find out. That's so weird. Okay, I don't know what happened. Just a second. Where's my page? Okay. Oh, too bad. Well, this is always a problem, the software installed in a computer. I restarted the computer at the very beginning of class, but it still does not work stable. It's not very stable. This is the problem with some softwares. Okay. In mathematics, we call it stability. When you design something, okay, whatever is the equivalent of something, if it be disturbed a little bit, can this machine still work stable, right? So if so sensitive, then it's not good product. Okay. Anyway, so we have to find out critical points first. Okay. So the partial derivative, so you have to solve these three equations. Okay. When you differentiate, you will get, let's go, we remember the function, right? So find the partial derivative, the first one with respect to x, and that is going to be 1 plus y times x, okay? And the partial derivative of the function with respect to y, I will get the 2x squared y. 2x squared y is be 2x squared. Then that will be 2y. Okay. Right? Yeah. So the first, the function, remember the function. The function is going to be, if you multiply this out, is 2x squared, 2yx squared plus y squared. So when you differentiate with respect to y, you get 2x squared plus 2 plus 2y. Okay? When you differentiate with respect to x, you can get this. Okay. So so you can multiply this out. It's 4x plus 4xy. Okay. Now when you set this to be 0, I think the trivial solution would be x equals 0, y equals 0. That's obvious. Okay. Right? When x equals 0, and then the y is going to be 0 too, right? Yeah, if you have a pen, you can try to solve this equation. You have to grant all the possible solutions. So we can assume that, you can assume that x is not going to be 0, right? If x is 0, the second equation tells you y is 0. So if the x is not going to be 0, the first equation will be x plus y is going to be 0. Okay, so that implies, right? So here, if x is 0, if x is 0, then y is going to be 0, right? By the second equation, that's equation 1, equation 2. Okay, so if x is not 0, then this is by the first equation. And so y is going to be -1. Great. Once y is -1, then x squared equals 1. It's by the second equation, right? Because x squared plus -1 equals 0. So then you get x equals plus minus 1. How many solutions you're going to get? You're going to get three critical points. Okay, 3 critical points, 0, 0. Okay, you get 0, 0, right? Okay, and you got 1, -1, and -1, -1. Those 3. So we have to check one by one for each of them. And so there's it's called a second derivative test. Okay, this is in the this is a section. It's page 999. Okay, page 999. So you look at this look at the second second partial derivatives. Okay, then you look at the matrix. If the matrix, there, you can find out, but I hope you understand why that is true. So first of all, let's find the partial derivatives. Okay, this is the theorem on page 1001. Okay. So we find all you have to do is, we find the second derivative. Okay, the second derivative, let's go back to the first derivative. The first derivative is going to be, here 4x plus 4x times y. So when I differentiate with respect to x, I get a 4 plus 4y. Okay, 4 plus 4y. This should be the same, and doesn't matter which side is first. Okay, that would be 2. Let's when I differentiate with respect to y, okay, and I got 4x. Okay, I got 4x. 4x and plus, no, nothing else. Yeah, just 4x. Okay. Then I differentiate with respect to y. I got 2. Yeah, I got 2. So this is you will get a kind of matrix, So in linear algebra, we will have to determine when the matrix is positive definite, when be not, right? So the matrix, the first one is fxx 0, 0, fxy 0, 0, fyx 0, 0, fyy 0, 0. Okay. If you took math 171, you should know what is that, right? So when y is 0, okay, when x is 0, and that is 2. So this is a positive definite matrix. Okay, so that's the first case. The second case, I get 1, -1, right? Okay, so when x is 1, y is -1, this is 0. Okay, when x is 1, y is -1, this is a 4. Okay, 4, 4, and that will be still always 2. Okay, and then finally, I write down it's -x. Okay, let's see if we get same result. I think the only difference is here's -4. All right, so let's take a look at those 3 matrices. I think the first one is a positive definite. Okay, so if you look at the D, okay, see of course you don't need to understand that, in the book it says that the first component, the fxx is 0, then the determinant of D should be positive. So the determinant of D, it's going to be 8. It's a positive, and this is going to be negative. Okay, -4 for 16. Here is also -16. Okay, and also 4 is positive. This component is positive, and this actually is positive. So 4 is positive. So in this case, this is a positive, right? So in that case, this is a local minimum point, local minimum. Okay. If you talk about point, then local minimum point. If you talk about the value, you get the local minimum value. Okay. When D is negative, look at that. When D is negative, it says that it's not a local maximum, local minimum value. Okay, it is not going to be local maximum, local minimum value. Then what is that? Okay, but this could be the center point. Okay. Yeah, this gave you the set point. Okay. All right, so now it's not complete yet. We want to find the local minimum value. The local minimum value of the function, you have to clearly state that that is a value, so called ff0. Okay. And since the function is, yeah, you just plug 0, right? So it's actually is 2, 1 plus 0, 0 square plus 0 square, which is 0. Okay, so the local minimum value is there. Center point, okay, you have to mention center point of the function. Then you have to mention that center point. Center point is at plus minus 1 and a negative 1, okay, at those points. So in the three-dimensional space, you can write down those 3 points, coordinates, right? With the first one, when x is negative, it doesn't matter. So y is negative, right? So actually is going to be plus minus 1, negative 1, and the third component is always going to be when you plug plus minus 1 for x and negative 1 for y, so you always get the 1, okay? Yeah. So there are 2 set of points. All right. Now, on the sample test, the very last one, it's about polar coordinates. Well, spherical coordinates, polar coordinates. Okay, we should know about the polar coordinate. Polar coordinate essentially not polar, cylindrical coordinate. Cylindrical coordinate essentially is a polar coordinate. Okay, so the idea is simple. Cylindrical coordinate. Okay, how do we define the cylindrical coordinate? Well, you have a circle. Okay, so so-called cylindrical coordinates is like that. Every point in the space, you draw the cylinder. Okay, you draw the cylinder. So you get the points here. Okay, then you use this angle, use the polar coordinates here for that point. So that means this radius is r, right? Then here's a point x, y, z. So x can be written as r cosine theta, y equals r sine theta. Z is still z, so that's so-called polar coordinate, cylindrical coordinates. Okay, so let's review. Right? So spherical coordinate. Okay, spherical coordinates is for in the space. Okay, take an arbitrary point in the space. You draw the sphere. Once you draw the sphere, then you can project this point here. Then you also draw this line. Okay, this is the phi. That's gonna be theta, and this will be rho. Okay, then then x is gonna be. Okay, x is going to be, no, this will be r, right? R is coming from the rho, right? That's be sine phi. So it's going to be rho sine phi. That is actually r cosine theta. Y is coming rho cosine sine, still sine phi, and sine theta. And z is going to be rho cosine phi. Okay, so those are the coordinates. And the rho is rho squared is equal to x squared plus y squared plus z squared, okay? Right, so that's the picture. And now if you are given if you are given the angle, okay, this is r theta z, which is 1 pi over 3 and the square 3 in cylindric coordinates, okay? And you want to convert it to change it from the spherical to change it from the cylindric to spherical coordinates, okay? Find the spherical coordinates, okay, for the same point. So all I have to do is to get x, okay, equals r cosine theta, y equals r sine theta, and z is still equal to z, okay, which is negative square 3, okay. So cosine pi over 3 is cosine theta, it's 1/2. This is square 3 over 2. Okay. So you get a point in the cylindrical coordinates, right? Then you convert it to, and then you express in the spherical coordinates, rho sine phi cosine theta, right? It's a rho sine phi sine theta. It's a rho cosine phi. Now, how do you solve this part? I think you have to find the rho first. Rho is x squared plus y squared plus z squared. So which is going to be, which is going to be 1/2, okay, which is going to be 1/2 square 3 over 2 square plus negative square 3. Okay, the first term is 1, the second term is 3, so it's 4. So rho is 2. Okay, so once you get 2, then you can determine phi, okay, because by the third equation, it's 2 cosine phi, right? The third equation, that's for z. So then cosine phi is going to be negative square 3 over 2. And what is that phi? This is a phi must be greater than pi over 2, right? Phi is between 0 and pi. So the only solution you're going to get here, I think phi is so phi is going to be pi minus pi over 6. Okay, so that is a phi. Okay, how do I get that? Okay, well, this is another story, right? You have some angle here, that's a phi. Okay, then you find a reference angle. So cosine of a reference angle is always going to be the absolute value of the cosine phi, which is going to be square 3 over 2. But I remember cosine pi over 6 is going to be square 3 over 2. So that's why I end up with, the difference should be 2, it should be pi minus the reference angle, give its original angle. Okay, so once you get this, then sine phi, okay, sine phi is going to be 1/2. Okay, so we go back to here, sine phi is 1/2, and the low times sine phi is going to be just 1. Okay, the low times sine phi is going to be 1. So the problem is then those two equations become simpler. Okay, let's go back to the equations, right? Cosine theta is going to be 1/2. This is going to be, cosine theta, and then square 3 is going to be sine theta. Okay, yeah, square root of 3 is going to be sine theta. Let's go back. Yeah, okay. So, and clearly theta must be equal to pi over, if both are positive, then theta must be between 0 and pi over 2. And clearly that's going to be theta, it's going to be pi over 3. Okay. So now you get theta phi and the rho. So that's why you solve the problem. Okay. Yeah, so you can say rho phi and the theta is going to be 2. Okay, pi over 5 pi over 6, pi over 3, for example. Okay. Phi and the theta is all, this doesn't matter. So I have to say that this is just a sample exam. So I cannot cover all, there's a possibility. Couple of problems will be modified. I mean, the modify means like last, the one, like a problem number 13. The sample test maybe ask you to find the maximum minimum value and set the point. Okay, and then, but it's possible. I probably ask you to find, we still have one section should be covered, like, use a Lagrangian multiple to find the maximum value around the circle instead of in a domain, okay? So there's a possibility. So I'm going to discuss in the very last class about this, possible as a problems, okay? So here, let's go over again, let's, yeah. So I'm going to talk about sample final exam 2. Okay. So given equation xy plus yz plus zx equals 11. Okay. Find the tangent plane to the surface. Okay, at 1, 2, 3. So 1, 2, 3 indeed is a point. Okay. The reason is you double check that 1 times 2 plus, yeah, this is a plus. Okay, 2 times 3 plus 3 times 1. So 6 plus 1 is 11. Yes. Okay. Now, if you have a function, okay, the function is in three variable. Okay, if the function is in 3 variable, and then this is a level surface. Okay, so so this is the level surface, and when you change it, let's put a constant here, right? In general, okay. So the level surface, it could be several levels. Okay, depends on the value of the k. Okay, so you have a slice in the space for different value of k, as long as the function is given. Okay, so the very important thing is the gradient of the function. Okay, is always perpendicular to the tangent plane at the point x, y, z, okay, on the surface. Okay, so if we choose a particular point, and that could, okay. And that will be the gradient. Okay. So that's the key part. Okay. If you know this, then you can solve the problem quickly. If you keep looking, when taking test, for example, if you keep looking at the textbook, and that takes too much time, you're not going to finish it. Okay. So our function f is xy, yz plus zx. So the gradient of the function, when you differentiate with respect to x, and that is y plus z, differential with respect to y is x plus z, differential with respect to z is y plus x. Okay, so we have to evaluate at this point 1, 2, 3. Here's a 5, x plus, right? It's a 4, y plus x3. Okay, so this is not a unit vector, but it is perpendicular to the tangent plane. So to find the equation for the tangent plane, you just needed to describe an arbitrary point on the tangent plane. So the arbitrary point, this is arbitrary point on the tangent plane, minus the point on the surface. This will be the tangent vector. Okay, and then should be perpendicular to 5, 4, 3. This, okay, that's all we need, right? So we will get x minus 1, y minus 2, z minus 3, 5, 4, 3 equals 0. I get 5x minus 1, 4y minus 2, 3z minus 3. Okay, it's parentheses, not that. Okay, so this is an equation. You don't need to modify it. All right, we must know how to, we must understand how to iterate the integrals. I change the order. Understand the iterative integral, okay? So the second question is sketch the domain, okay, of the integral, okay? This is called, sometimes called region. Integration of the double integration, and changes the order of the integration. Okay, so we have a okay. Now, what does that mean? Okay, if you understand how do we get the iterative integral, then you understand this. Okay, look at this. The outside, the variable is x. So that means x can be anything between 0 and 1. But for the fixed x, there's a restriction for the y variable. Right? The y variable is the lower bound is 0. The upper bound depends on square root of 1 minus x, depends on x. Okay, so look at the equality. If you look at this equality, you end up with a circle, right? So squared, and then you get x squared plus y squared equals 1. So that's a circle, but x is not a negative. X is between 0 and 1. So that will be a portion that x is between 0 and 1. Okay, but y is also positive. So this is only half of the, okay, this is a domain. Okay, so this is a domain. Okay, so once you understand this, then so we are here actually is using the vertical lines, right? But then you can get the horizontal line. So for So switch that for any y between 0 and 1, right? X is the lower bound for x is 0. Upper bound, you solve that above equation, you get 1 minus y squared, right? So that's why the integral becomes 0 to 1 dy, and from 0 to 1 minus square x, and f of x, y, and dx, okay? I want to see statement like that, besides the integral. Don't just put the change the order. So I want to understand, how do you think of, okay? You can describe the same domain in two different ways, okay? You mentioned the y variable first, then x variable is restricted, okay? Okay. Yeah, you have to show much detail as possible. Evaluate the triple integral. 12y dv. Now this e is described by 3 inequality. 3 inequalities, okay? So y is between 0 and 1 and 1 minus x, and z is between 0 and 1. Okay. Actually, you can write down this, if the order is already in this given in this order, so actually you can write down the triple integral directly. Okay, x is between 0 and 1, so I put dx here. And for each x, y is between 0 and 1 minus x, so you put dy here. And then for each x and y, z is between 0 and 1. And sometimes you can have y plus x, okay? So this is a 12y, dz, and dy, okay? Yeah, you should be very careful to look at the dependency from left to the right. Okay, sometimes I change the order, but don't forget the last variable depends on the previous two variables. Of course, in this case, z only depends on y variable. Okay, the upper bound. Right. So now is a step by step, and this is a 12y is independent of z. That's why 12y, and then you have a y square here, dy and dx. And then the antiderivative of 12y squared will be 4y cubed, right? When you differentiate, you get 12y squared. Okay. And then finally, you will get 1 minus x cubed dx. Now, I suggest you to use substitution for this problem, because otherwise, when you expand it, it's as many terms. So you let u to be 1 minus x, du equals negative dx. Okay, so this is going to be the integral. When x equals 0, u is 1. When x equals 1, u is 0. 4u cubed negative du. Okay, and if we change the order, you get 4u cubed du. So the antiderivative of this function just u to the 4th power. So the answer is 1. Now, usually, the triple integrals can be evaluated step by step. First was double integral, then a single integral. Okay, it's not necessary you project the whole region into, in general, you see here's a solid in the space, right? What you do is, for example, you project it to the this is a projection, okay, it's a shadow. So this is a D, okay, that's a E, okay. Then for any point, you draw the vertical line passing through the solid, and then you have upper bound for the z, lower bound for the, here's the x and y. Z can be between, between h, x, y, and h1, let's say h2, xy, okay? Then the iterative integral, the triple integral f dv can be evaluated using the double integral here first, and that is dz f x y z, and these are between, okay, and then dA, okay, dA is in the domain D, okay. So step by step, right? So this is the idea. In general, especially when the region is inside the cylinder, right? Then you should do this first. Okay, you cannot write down 3 iterative integral in the one step. Okay, especially when this is it's a domain in the a region in the inside the cylinder. It's bounded by cylinder. Right. In particular. So if it is a disk, so we can a typical example is region E. It's inside the cylinder. Yeah, x squared plus y squared is less than 1, and z is between and 0, for example, and the square root x squared plus y squared. So this actually is a cone-like, okay, but inside this cylinder, okay. This is below the cone, okay. So this area, okay, yeah, this region, yeah, okay. So if you want to evaluate a triple integral of the function, let's say, doesn't matter, it's a z or x, right? Let's use a z, for example, dv, right? In that case, step 1, okay, you needed to describe, this is a d, right? D is the projection of the solid onto the xy plane. There will be just x squared plus y squared less than or equal to 1. So you go to the double integral first, then iterative integral. Then you look at the direct z is between those two variables, right? So it's dz, then dA, okay? And so the entire derivative of z is half of z squared. Oops. And evaluate the two endpoints. Okay, so you will get 1/2 and x squared plus y squared dA. Then you use polar coordinates to solve this problem. Okay, now you can, if you get very familiar with that, you can skip that step. It's just write down all the terms. Here's r squared r and the d theta dr. Okay, d theta gives 2 pi. 2 pi divided by 2 is just pi. Okay, then the antiderivative of r cube is just quart times r to the 4th power. So that is that is how do we do that for the triple integral. You cannot, in many cases, you cannot write down 3 iterative integrals. Yeah, 3 integrals directly. you can step by step, double integral, one single integral, then finish a single integral, then you work on the double integral. Like in this case, it's better doing this way. All right. And the next one is about evaluate the integral of some function along the curve. Okay, C is x equals 2 cosine t, y equals 2 sine t, t is between 0 and pi. So this curve is already parameterized. And my opinion is just the semicircle, but it's start from here. Okay. The radius is I equals 2. Okay. Remember, in general, we have the formula, right? If we have a C, we have a function, x and y, and ds, right? So the formula is, if we can parameterize the curve, this will be f of x of t, y over t. And the very important thing is what is ds? ds is x prime t square, y prime t square dt. And that is the ds part. Okay. Now, for our function, right, x prime t equals -2 sine t, y prime t equals 2 cosine t. So clearly the function, okay, y squared ds is going from 0 to 2 pi, y is going to be 2 sine t squared, right? And the ds here is going to be -2 sine t squared, 2 cosine t squared dt. So which gives you a 2. So 2, 2, I have 8. And this definitely is a positive, right? So you have to change to the w. 1 minus cosine 2t dt. Okay. So let's simplify a little bit. I'm going to put a 4 here. 8 divided by 2 is 4. Then the antiderivative of 1 is t. Antiderivative cosine 2t sine 2t divided by 2. And divide by, right? Evaluate between 0 and pi. Okay. And I think the second part is 0 because sine 2 pi 0, sine 0, 0. So it's going to be just pi. Okay, so it's 4 pi. All right. I probably want to modify this problem. Okay. So we want to, I want to evaluate this surface integral of z ds. What is S? S is the triangle, okay, in the space with vertices 0, 0, 0. That's P. Q is 0, 3, 0, and R 1 and 1 and 1. Okay. So Yeah. Yeah, at the same time also want to find the area maybe. Yeah, I do a little bit more additional. Yeah, find so this is a triangle in the space. This is one point. Here's another point, and this is a point in the space. Okay. Yeah, it's harder to draw, but it is a point in the 3 dimensions. If we project it to to the xy plane, you get a shadow. Okay. So here's x, y, z, and this point will be 1 and 1, 0, right? And here's a 0, 3, 0, and this is a 0, 0, 0. Okay. So in the xy plane, now you can view it as a graph, right? You can view it as a graph, right? A special graph. Okay. So what is a D? If you look at the D careful, right, is in the xy plane. It's a 0, 0, and here's 3, okay? And then there's a point 1 and 1. So that is my D. Okay, that's a D. Yeah. Okay, if you want to color it, that's my color. Okay, that's a D. That's a D. Okay. So the triangle can be viewed as a graph over that triangular domain. Okay, S can be viewed as the graph of some function f over the triangular domain D in the xy plane. Okay, the D consists of 3 angles, right? Okay, so first thing we have to do is find the equation for the plane in the 3-dimensional space so I can get the function of x. How can I get the plane quickly? I think we can find a normal vector. Okay, this is a P, that's a Q, that's R, right? So the vector PQ is going to be the difference of those 2 components, 0, 3, 0, okay? The vector from P to R, the difference of, yeah, this is also just 1 and 1, okay? So the cross product, okay, it's going to be IJK 0, 3, 0, 1, 1, 1, okay? Let's calculate. And then I got the first one, I guess. The first one I got 3i, okay? Then I got 0, right? Because when I remove this, I get 0, 1, 0, 1, okay? And k, I think it's, I get negative 3k, okay? Yeah, negative 3k. So it gets 3, 0, negative 3, okay? Therefore, the equation will be the equation for the plane. If you know the normal vector, right? Normal vector point to the direction, some direction like that. Okay. Okay. I don't care about this. So here's an arbitrary point x, y, z. So you get a vector. It's a tangent vector. Okay, it's x, y, z. You know, subtract with 0, right? and then the product should be 0. So I get 3x minus 3z equals 0. So actually z is going to be x. That is my equation for the plane, okay? Which is the function fx1. Okay. Now you can, so for the surface integral, right, you have to find the ds, right? So ds is going to be fx squared plus fy squared plus 1. So when you differentiate, it's 1 squared plus 0 squared plus 1, which is square root 2. Okay. And this is a dA and the dA. Okay. Finally, we get the surface integral of what this is. It's the integral of z. Okay. So integral of s z ds is going to be the double integral of the d. Z becomes x at the square root 2 and the dA. Now you have to work on this triangle, right? 3 and here's 1 and 1. How do you evaluate this triple integral? A double integral over this triangle. Over this triangle, well, you have to use you have to find the upper bound for, use a vertical lines. Actually, you have to. There are a couple ways to do. If you want to use a one single integral, you have to find the equation for these two lines. Equation for this line is y equals x, right? No problem. Equation of the other line, it's not easy to find out. There's a slope. Yeah, let's try to figure out. The slope is negative, right? The slope is negative, negative 1/3, not negative 1/2. Okay, the difference of y variable 1, the difference is, negative 1/2 x. And what is the y coordinate? Okay, you have to add that as a constant here. Okay, you have to add that as a constant. Can we figure it out? When x equals 3, I should get 0. When x equals 3, I should get 0. So that's going to be 3/2. Okay. So that's it. So this is a two equation with a line. And I suggest just use one single integral. So choose for an arbitrary y between 0 and 1. So the x value is going to be, I'll use a horizontal line, right? What is the lowest? This is y, right? The upper bound for the x is y equals negative 1/2 of x plus 3/2. So I needed to solve for x. Okay, I multiplied both sides by 2. Okay, then I think x is 3 minus 2y. Okay, and here's x dx. Okay. So the antiderivative of x is half of x squared. Okay, so it will be x squared. Evaluate the two endpoints. So you will get 3 minus 2y squared minus y squared, and the dy. And then evaluate, multiply this out. That's 9 minus 12y and 3y squared. Okay. Then you find the antiderivative of each of them. Okay. And the answer is 9 minus 6 is 3. 3 plus 1 is 4. So that is the answer. Okay. It's a little bit complicated. but we can work out. So that's a possibility. You're given a surface integral of the triangle over the triangle. Now, how to find the area of the triangle? Okay, find the area of the triangle. Okay, the area of the triangle is this just the surface integral of ds. Okay, right? You can use this one to find the area, and we already got this. It's going to be the double integral of the triangle d, right, over square root 2d dA. So you just need to find out the area of the triangle in the base. But the area of the triangle in the base, you know, you already know that because this is a triangle. Here's a 3, right? Here's a 1, right? The height is 1, and the base is a 3. The height is 1. So that will be 3 square root 2 over 2. Okay. Now, if we do not do that without using integrals, we already know the remember, right? We go back to find the area you can without using calculus, right? So you get yeah. So you have 2 vectors here in the space. So when this is a right. So here's a P and a Q and P and R, right? So you have 2 vectors, right? Remember this, right? That's going to be 0, 3, okay? P and R, 1 and 1, right? And then we have the cross product, right? It's going to be I think it's going to be 3, I forgot the sign, 3 and the negative 3, I guess. 3 and the negative 3. 3 and okay. So according to linear algebra, okay, the area of the triangle, the surface, is going to be half of the length of this cross product. Okay. Okay. So it's going to be that. And then you can take 3 out. So you will get this. It's the same answer. Okay. The reason is in the space. Yeah. In the space, let me repeat again. You have a vector A, you have a vector B. In the parallelogram, the area is the length of the cross product is going to be the area of the parallelogram. So for the triangle, just divide by half. So that is going to be the area of the parallelogram, okay, in the space, okay. This is actually, if this is angle theta, this is actually the length of vector A times the length of vector B sine theta. So the length of B times sine theta is actually gives the height of the parallelogram. So this is the height. You know, the one side of the length times the height is given the area of the parallelogram. That's what we learned in middle school, right? Yeah. So I stop here, okay? And we will. We have one more review class. Go. Okay. Bye bye.